Okay, so we're going to talk about a couple different topics here around and for section three for topic three. So they're gonna. what I'm going to do is I'm going to put them all into this one video. All right, because they're fairly short in duration, but I want to kind of give you, just. But I do want to touch upon this stuff. Um, just a quick heads up: the videos that, excuse me, the slide decks. If you go to the class site and you look at the slide decks, what you'll see is I've actually have hidden some of the slides. I'm just going to talk about in the videos here the slides that are going to be really important that we're going to want to cover content wise, right? So this first piece we're going to talk about is something called data structures. All right. So this idea of a data structure, what a data structure is, it really deals with the internals of the database. Basically, it's uh, the way we organize the insides or the structure of the database, be able to get to data. So there's fundamental um, computer science concepts that come into play with this. So we're going to talk about this. Um, the idea is, the design of this stuff is important because, quite frankly, it's one of the things that make databases work. All right, the idea of what in these data structures, the utilization of these data structures, it's aimed at providing a flexible data access based upon, the knowledge of the data items, and we're seeing things like the primary keys, the secondary keys, all these things, the way the actual database works behind the scenes. Once again, this is all being done, implemented through the DBMS. All right, so there's a couple different structures we're going to talk about here. So we're going to talk about this idea of a linked list, something called an inverted list, and something called a B tree. All right. So the way the actual if you crack open a database, if you go actually look at the files and how things are going, what you'll see is there's the way you get at the data, the way we're able to access the data and find data. Because you think about what you've got millions of rows of data, and how do you locate something within that? So there's a whole idea of different kinds of pointers. All right, the idea of and a pointer is just that. Basically, it's a key that points you to the next thing you're going to look at. So we have logical pointers. The things that some if we have a list of items, a logical pointer would point to the next item in the list. All right, so you have 50 things in the list. You start with one, you go to 50. All right. Ultimately, these logical pointers become translated into physical addresses. All right. So that's something we use as a means of being able to identify data. There's other kind of variants of this. So we'll see things like we call relative pointers. So the idea is what you can do is you can calculate an offset. All right. So you've got say 500 items. You can do a calculation and try to figure out of those 500 items, which number are you? All right, and it gives you, it'll give you the position of the file, of the record in the file by relative to the beginning from the beginning of the file. Um, relative record numbers. The idea is records are numbered from one to n in the system. All right, so logical pointers, and then physical pointers is really the actual address of something. So if you look at the way, and we'll talk a little bit about data structures and data storage, everything, if you look at these disk drives, so you look at your hard drive on a computer, if you kind of were to pry it open and look at it, ultimately every place we store data has got an address. All right, think of it as a mailbox or a post office box. All right, where you've got a billion post office boxes. Each one of those boxes can contain something. All right, so what happens is the disk drive is really organized into a bunch of addresses that we can get to, and that's where the physical pointer. So the physical pointer will point to a particular address. We can go to that address and find something. All right. So this whole idea of pointers is a fundamental piece of these data structures. Uh, there's a concept in computer science, something we call a linked list, and really what all a linked is just simply a chain of pointers, all right, which gives us a record sequence of everything that's out there. All right, so we have a head of a list, which is the first record of the list. We have the tail of the list, all right, which is the last record. All right, and then we process the list going to the first record, seeing what the value is, and then the next thing we would see was the pointer to the next item in the list. All right, so think of a chain. If you look at the way a chain is constructed, think of it as a chain of items, where we can track it through. And then there's another concept, and this is a fundamental, once again, this not just simply limited to databases. This is a computer science thing across the board. But linked lists, we see this a lot. So we'll see it, we see an implementation of it within databases. Right? And there's a concept we call a ring, which is, a linked list with the tail points to the head. We can do a nut. So, the idea is these linked lists are, kind of a one way. You start from the start, you go to the back. You can also do a bidirectional linked list. All right. So you can actually go backwards. So you go backwards and forwards. So the idea is if you can do forwards and backwards, you can speed up access. So because if you're going through a single list, you're reading it serially. You're going from the start, going to the end. If you can read it backwards, you may be able to get to something faster. If it's something close to the end, and you start at the end and work your way back. Makes it more complicated, but it gives you a performance boost. All right. Or we have this other. So there's another variant of that kind of structure. But linked list is as I said, you would see it if you go into like formal computer science classes. There's a whole series of studies around linked lists and the way you implement linked lists and implementation of linked lists and being able to develop algorithms to work with this stuff. An inverted list is just another variance of it. Be able to be actually the idea of being able to get a better performance. So some of these variants we see, an inverted list is really just a linked list with some additional capabilities, additional functionality to speed things up. All right, so what we do is we index tables of pointers to be able to, especially when we're talking about large data sets. We talk a couple million entries in a table. This idea of having an index to be able to kind of develop shortcuts to be able to do things. That's what these lists and these kind of different structures kind of provide for us, like inverted lists. A B tree. So another one, and this is actually, you see a lot of this stuff in like Oracle. So Oracle databases are very much have been built around this idea of a B tree, or what we call a binary tree. All right. So the idea is you have a binary tree is you have a head, and you have two entries, and then each of those entries can be the head of two more entries, and so on and so on and so forth. So what you'll have is a what we call a hierarchy, layer after layer of a binary tree. So the idea is, one root, all right, with two children, all right, and each of those children potentially being a root for two more children. And so imagine just a hierarchy, all right. So you could do things like this idea of creating a balanced tree, all right. Or you can also, this idea of also the height, be able to how many layers or how many levels are in this hierarchy. All right, so there's some rules around this, around these B trees. All right, so non-terminal nodes can turn one pointers to indexes at the next level of the tree. Each item being indexed, and the pointers to the record occurrences of the index value. The idea is this structure can be used. You combine this with a set of algorithms to be able to parse and be able to quickly identify data. So instead of just going through the way these things are structured in such a way so you don't have to read every item, you can speed and accelerate your access. So these data structures are all the types of things that are all behind the scenes inside of these databases. So that's our kind of the first thing we wanted to first topic area around this data structure. So the other thing we have is the actual physical storage. All right. So physical storage is, ultimately all this stuff we see in a database, everything is physically stored somewhere. All right. It is, it's a representation of its data that's represented somewhere that you can get at it. All right. So there's a couple things, when we look at this stuff. We have different storage devices. All right. So we have disk drives. We have disks of different sizes and different speeds and different characteristics. Like you can have like your traditional computer disk is a spinning magnetic disk inside of it with a motor. Now what we've seen is, over the past 10 years or so, we've seen the rise of what we call solid state disks, which basically store data, but it stores it in like memory, as opposed to physically spinning a physical spinning drive. So we have a bunch of different things we can do. All right. The thing that's important to remember is there's a logical representation of it, which is then implemented on physical. So the idea is, on the logical approach, we do things the same way. So from a database DBMS perspective, data looks like data, no matter where it's physically stored. Right. As we go farther down into the structure, though, as we get closer to the physical, it starts taking on specific characteristics. So if I've got a hard drive, a spinning hard drive, the physical storage of that is different and is implemented in a whole different fashion than, say, a solid state drive. All right. The concepts we have here we call logical records. A record with a record describes specific instance of data values. And then all of these records are combined together in a data file. Ultimately, databases are stored in data files. All right, and data files are stored on some type of storage media, disk file, some sort of disk or memory, sort of solid state memory storage. What happens is that there's characteristics. There's different physical characteristics of storage, and then each of those physical characteristics will translate into different performance or access efficiencies, all right, which translates to speed. So some things are faster than others. So solid state drives are faster than traditional rotating magnetic disk drives, all right, which are faster than like floppy drives or faster than tape drives and things like that. So each one of these things, even though from a logical perspective, the data is still, you can access it no matter what media it's on. Physically, each one of these things ultimately translates into something ultimately is represented by how it is physically stored on some sort of media. All right. So some of the basic concepts here. This idea of primary keys. We talk about primary keys in databases. Primary keys are also how do we find this stuff in data. All right. And then we talk around the disk drives themselves. Disk drives are actually broken up into storage blocks. Because I think we had talked about with the previous section where we talk about this idea of a disk drive, a physical disk drive basically being a collection of boxes with addressable boxes. All right, so the data storage blocks are addressable. So the key word we look at on this is this idea of something being an addressable entity. All right. So, the idea is what you do is you break everything up, you drop them into these data storage blocks, and then you read the entire block. So you don't really, so from the efficiency perspective, you store the stuff in different ways. So for example, even if you're only storing a single character, that takes up an entire block. All right. And these things like block sizes, this is kind of an art around the databases. Block sizes will determine how much space it takes up, and the speed by which it can be accessed. All right, a lot of times what you'll see is fixed block size because what you want it's a mechanical process of getting from this from the other. So you don't want to have to be trying to figure out how big the data is. What you do is it's faster a lot of times to just simply allocate the space, put the data into it, and as your reads are, you're only reading like 5K blocks of data, 5,000 bytes at a shot. Boom, 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 boom. However many times you have to do it. All right. So but you've got a lot. You've got different approaches. Though that's one approach. With optimal, a lot of times you'll see, standardized on a single size. Though you can have variable size blocks, and certain scenarios where that becomes about approach. There's a concept. There's a something we call buffer. So the idea is that disk space, disk storage, physical storage is usually relatively slow, all right, in comparison. So it's from human terms, it's astonishingly fast, but in computer terms, um, disk storage, even solid state disk storage, is slow. All right, memory and compute are the faster items in the computer construction. All right, so there's a thing called a buffer. All right, so a buffer is a tool. It's a chunk of memory that's set up to really allow you to kind of align the relative speeds, high speed memory with relative slow speed storage, and be able to not wait. Because obviously, if a computer had to wait for all the physical storage to occur, um, it'd be slow. So this idea of buffering. If you add more buffers means you read more stuff and you can process stuff faster. All right. Record blocking is an approach where you can combine multiple logical records into what we call a block, so you can be more efficient in terms of accessing the data. And really, what you want to do is get it off the physical storage, get it into the memory, which you can operate very fast. All right. And then with this record blocking, we can say, what the blocking factor would be, how many records we store per block. So I do 1,000 records a block. When I read one thing in, I'm not getting it one at a time. One at a time would be slow. I read one block. I got 1,000 records. So some of the characteristics, sequential devices were like the oldest form of computing. All records are one stored one after the other in that particular sequence. Basically records going into a block being written to a physical disk. All right. If you want to reach the 500th record, you read the first 499. Direct access devices, DASD, means we can address individual locations, or we can go directly to something. We don't have to read all of the we don't have to read everything leading up to that. So direct access, so sequential devices are relatively slow. Direct accesses are faster. Most systems, most disk drives, give us the ability to do direct access, to be able to get to a particular, if we can calculate what the address is of something on a disk drive, which is really the secret sauce of what a database does. It can calculate, it knows where things are at, so it can figure out where the block is at and go directly to it. So we call the response time. So this has been the big challenge in computing for the longest while. How do you make this stuff go fast? We've made processors faster and faster and faster and faster. All right, so what happens is, since storage and disks and, is relatively slow, there's been a whole, things like buffers and all these other things. These are all different techniques, and it continues to evolve in terms of how do you make these things go faster. So the response times, we define it as, what is the amount of time it takes for something to be executed, something to be able to be completed. And your access method, your storage techniques really are the thing that drives performance. CPUs operate so much faster than storage devices. So, that's the weakest link, is really your storage devices. And that is, and what happens is, like, especially if you think about it, a spinning disk. One of the things is one of the issues you have with that is, even if your disk is going 78, or say 7,400 RPM, rotations per minute, there's an amount of time for that disk to come all the way around to be able to get to the read head, to be able to read something. All right. So what happens is the rotation speed, and where you physically store stuff, and the rotation of the disk is a critical factor. Even though it just says 7,400, 7,400 rotations per minute or second, it's still from a computer perspective, from a CPU perspective, it's pretty slow. And that is that's what we're going to talk about from a storage perspective. So the next topic we're going to talk about is this idea of what we call a distributed database model. All right, so this is kind of an interesting. This is has been an interesting idea. Most databases, as we see them, are implemented as one big system, a big central system, a big central database. All right, but there's an idea that has been really worked on for a long time and is not necessarily totally mainstream, but there's certain situations and certain scenarios where you're going to want, where there's an advantage to actually, instead of having just simply one database, distributing the database and different things and be able to treat it as a whole. All right. So theoretically, you should be able to get the data wherever you're at, wherever an organization is. And an organization, in modern times can be anywhere, can be anywhere on the planet. All right. This idea of a distributed database model allows us to do this stuff. There's specific technologies. The relational model, if we, this thing we've been talking about, this relational models assume everything is really kind of in one place. All right. So if you're going to be distributing databases, if you're going to move data all over the place, you still, even though physically the data is distributed, logically it's treated as one database. All right, so this logical distributed it's physically distributed, logically consolidated or consistent. Right. So the way these systems are designed is that we can have a whole bunch of different types of computers. So we can have mainframe computers and servers and mini computers and PCs and laptops and tablets and all sorts of stuff, and be able to have one database that's physically spread out all over the place. All right. Couple different ways we can do this. There's a couple practical ways to do it. So not every database, most databases are really just a single consolidated centralized database system. All right, that's the easiest way to do it. But there are a couple of practical ways people have come up with, organizations have come up with, to be able to deal with this stuff. One is this idea of one technique is what we call replication. All right. So what replication means is that there's two full databases, and what we do is we move data, we transfer, we replicate data from one system to the other. All right, so if you make a change on one side, that change is applied on one system and then transferred over to the other system. All right, back over. All right. Basically, you're doubling the size of it. So you're doubling the size of the database. The advantage you have, though, is that you have two. When this is implemented, you have two exact copies of the database. So replication becomes very important for things like disaster recovery. All right. So if you've got a situation where you can't turn the system off, what you do is you can replicate multiple copies of the database. So if you turn one system off, the other copies continue to operate. So replication is a pretty big concept, a pretty pretty big use case. Right? Another distributed technique is something we call partitioning. Right? Partitioning means is we split the database into different pieces across different systems. So like one system will take one piece of the database. So they'll have five. You break it up into five pieces, and one computer will run one piece of it. Another will run another. Another will run another. So you have five computers running five pieces of the databases. All right, so there's advantages in terms of speed. There's advantages, but once again, this is something that has to be well designed. All right, and it's not something that is a general. You don't take the idea of partitioning very lightly, because it really has to be well designed. But you see a lot of times, you'll see combinations of this replication and partition databases, for situations like disaster recovery and getting high availability and making sure that you can, you keep your data accessible, with high performance. So with partitioning, you can do what we call horizontal partitioning. So what that means is that you would take a horizontal positioning is rows. Basically, you split it by rows. So what happens is one system will have rows 1 to 100, and another system will have rows 101 to 5 million. Right? And that would be a situation where you'd want to keep the most recent 500 systems in one system, and the other ones not quite so much. All right. Conversely, we have what we call vertical partitioning, which is where you can split it vertically. So what will happen is you'll take the first 15, instead of doing it by records, you do it by fields. So you'll take, say, you've got 100 fields in a table. All right. So the first 5 you'll put in one system, in one partition, and then the 95 you'll put in the other. So, one of these things, there's different circumstances where these things will make sense. Once again, it's also driven by the individual business scenario, how we're doing this stuff, what you're trying to do, what's the performance, you know, um, you know, in certain circumstances, you can get some real advantages of it. In other circumstances, it can complicate things to a point where maybe you're not getting much of an advantage. Right? So that's this idea of partitioning. Um, the biggest challenge we face in these distributed databases is this idea of what we call concurrency. So one of the things, we've talked about this with this idea of databases. Databases, the whole role of the database management system is to keep the data correct and keep it consistent. All right. So the idea is if you're doing an update, all right, only one thing can be updated at a time, and everything gets locked. So what you'll do is when we're doing an update, what it'll do is we actually create something called a lock. And a lock is, okay, only that one transaction, one, user can make a change at a time, because you can't have two things happen. If you have two things happening at the same time, who's correct? All right. As we get into this distributed model, that actually makes that's a challenge no matter what, because if let's say you get thousands of users all trying to do the same thing, so trying to that's a big issue. That's an issue there. Trying to do this stuff concurrently across in a distributed fashion is makes it even more complicated. So these implementations, these distributed systems, distributed architectures, your database architectures, are really pretty sophisticated stuff. So like I said, you'll see some implementations, some things like, for example, replication, or for high availability, that's there, but you don't necessarily see as a general purpose function. We talk about recovery, in distributed databases. Once again, as we said, databases themselves, their job is, and the pieces that we have in these systems are designed to keep these things consistent and operating. Trying to recover these systems is also, it's not just simply concurrency. It's also, if you try to do a recovery of these things, so difference, you're adding layers of complexity in terms of being able to track what's happening, what changes are being made, what changes are being registered. If something happens on one side, on a whole nother system, updates are happening there, and then something was to happen, how do those changes get replicated or sent back in? So there's a lot of different techniques that are in here that all come into play. But the bottom line is distributed databases are complicated. All right. So there are some advantages. A lot of stuff is performance. Having localized systems. You can do fairly small databases, seem to work pretty well. Response time may be faster working on a subset of data, and if you're only working with summary data, being able to distribute data and keep it operational. There can be some advantages around it. The disadvantages, though, and there's a number of them, what we call economies of scale. Basically, instead of having one computing system that can do a whole bunch of stuff, you're having implementing multiple hardware, lots and lots of hardware. All right. Large computer systems. This whole idea of economies of scale really goes back to large systems can do work faster and cheaper than a whole bunch of little systems. All right. The overhead, the additional costs of replicating the hardware, the software, and all this other stuff. You might not necessarily get a communications advantage. And then, I think the general concept is one of the complexities of these systems. These distributed systems, having worked with things like an Oracle. Oracle had something they designed called uh, uh, they had a clustering technology, um, and it did work, and but it was also extraordinarily complicated to set up, and they keep it running. All right, so what they called rack was the name. I don't recall something real access clusters, something like that. But anyway, Oracle had something like that, and it was extraordinarily complicated. It was a distributed database model, but it was a very complicated uh, system to keep going. All right. And so finally, the last topic area I want to touch base on here is some other approaches to databases. All right, because there's not. So we've talked about the relational model, which has really been the essence of what this course has been about. But there's some other ones. We've talked a little about. There was stuff that was historically related to like hierarchical databases and network databases, which were the precursors of relational. Now we've got kind of a new generation of some different database technologies that are out there. So I just want to kind of introduce some of these concepts. All right. So the first one is this idea of an object-oriented database. All right. So this is a kind of came into play a couple years back. Especially when Java was introduced as a programming language, this idea of using an object-oriented design. So this is an application of the whole broader computer science concept of object-oriented applied into a database. So what you do is you kind of you organize your data into what we call objects, all right, which all have different relationships, which they can then be manipulated, all right. And there's within object theory, well, things attributes and methods and relationships association. So it's sort of it's an approach. It's an overall. It's a broadly applicable computing science approach, which has a specific implementation with databases. So, if we look at our traditional relational database models, here's our the things we're focused on. So it's persistence and efficiency and concurrency, reliability, and an SQL as a query language. In object-oriented, we have this idea of a complex objects with have identity, encapsulation to be able to hide characterizations and attributes, providing access to what we call types and classes and class hierarchies. So there's a lot of, so there's particular, the thing about object orientation is a particular focus, a set of rules that go around it. So it's not limited to databases. This is what we're talking about here is an application of this into a database sort of environment. All right. Complex objects, an object is formed by simpler ones, so you kind of you can create very simple objects and then combine them together to create larger, more sophisticated types of structures. All right, so the kind of the key thing that kind of come with this in databases is something we call like the object identifier. So a record can be an object, where you would create an object for a particular record, or you collect things together. It's definitely a little bit of a different animal than relational. But what's happened is this idea of an object-oriented approach has actually been baked into a lot of these databases now. So like MySQL actually has some object-oriented functionality capabilities that are kind of aligned with it, that are baked into it, which can be used if you're so inclined. All right. One of the key concepts around this stuff is encapsulation. The idea of hiding all of the complexity of an object, all the stuff it's actually doing. You don't need to see it. All you need to know is you create an object, and it has certain defined things it can do, what we call methods. All right, and what we do is we call those methods. Okay, I want to change something, or I want to do. So from a utilization perspective, it's very simple. You say, okay, I'll create an object, or what we call instantiate the object, and then I can do stuff with the object. All right, but it's only through these methods. So you can't go in there and it simplifies and controls access to doing different things. The other thing we run into, things like data types and classes. So there's different data types, different object types. This is all part and parcel of object theory. All right. This is kind of a pictorial representation. An object or a class contains an object. Objects have value. Class has type. Types describes what the value is. So this is kind of a relationship between data types and classes. All right. So these are the fundamental building blocks of object theory across the board. All right. And as we said, what it does, it really the implementations we see, it's really kind of an extension of the relational databases. So Oracle has object extensions that they've baked into it, and MySQL has object extensions that they've baked into their SQL. So you can do SQL stuff, or you can just do your typical relation stuff. And what they've done is they've kind of have created some new add-ons to SQL to be able to do some of this stuff, to be able to work with it. All right. So it's like I said, it's not for everyone. It's not something everybody does, but it's something that can be done. All right. There's another concept we call NoSQL, all right, or not only SQL, which is the next other big thing. We talked about this idea of big data. All right, not just big data, massive data. All right, and the idea what happened was databases were great as we're dealing with data sets in the millions. All right. As we get into the billions and beyond, all right, this becomes much more challenging. All right, so really what's happened is there's a whole new generation of technologies we call basically no SQL, or as it's described as not only SQL. So it doesn't replace SQL. It's really as an extension or a complement to it that lets us work with larger and larger data sets. All right. It has some different characteristics to it. Obviously massive size, the ability to run things in parallel. Instead of having a single processor doing things one at a time, be able to chain a couple thousand machines together and kind of chew through a massive set of data. If you can imagine like a giant army of locusts chewing through a wheat field. That's kind of the idea. That's kind of the imagery you want to take with this. It's designed to be simple. It uses simpler structures. It's not as sophisticated as SQL, but it has a purpose. All right. So it's a whole new set of data. It's dealing with data of any enormous size. It does not replace relational models. It is anything. If anything, it works as a complement with relational models. All right. So a couple things we see is this idea of stored column databases. So you've seen a couple different, and there's a bunch of different techniques and different things. Google has done a bunch of work around this. Google's done a lot of the stuff in the big data area. So their big table, MapReduce, which was a Google tool to be able to process large amounts of data. The big thing, one of the big things it does is this idea of a key value store. So it simplifies it. So instead of having like a record that has, say, a bunch of fields or attributes on a per record basis, basically you got two things: you got a key, you got a value. All right. So the structure is simpler. It's simpler and larger. All right. And it can be used all sort. There's a couple different things we see. This idea of being able to do the store as documents, be able to store it in graphs, which is like a mathematical model, what we call graph databases. So there's some new techniques that are out there, but that's all part and parcel of what we call the NoSQL data management domain. Talk about MapReduce. Basically, it's an open source solution, so you can actually just download it and run it yourself. Something called Hadoop. All right. So the idea is it has a set of fairly simple tools So the algorithm dealing with this stuff is it's pretty simple because the idea if you're going to scale to billions, what you want to do is you want to create something very simple and just do it again and again and again and again. Right? So that's really this whole thought process behind MapReduce or the actual implementation. If you take a look out there, something called Hadoop. All right? So the idea is you can chain thousands of machines together in one of these Hadoop clusters and be able to process petabytes of data. And it's been fairly it's been a pretty effective model, especially as we're dealing with these in the big data set world. So just a couple little bits of information. It actually has something called one of the things Google defined is something called a Hadoop distributed file system, which is basically how it stores the data. Assumes it's an inexpensive, unreliable commodity hardware. So basically, PCs or actually cloud computing. So where a lot of this stuff is really coming to play is like with cloud computing, and it uses this HDFS will use replication to making multiple copies of different things. So the idea is, okay, if I lose one piece of data over here, don't worry about it. I've actually made multiple copies of it. All right. So basically the idea is kind of, and the thing that makes it unique is this idea of, data with servers that are used both for both the storage and for the computation. And this idea of what we call key value. So this is kind of the fundamental stuff. All right. So it's, the idea is, high scalability, availability, performance, be able to work with, be able to scale large numbers of simple computers. But it's also not the same thing as a relational database. Right? There's circumstances that you would use this stuff, which are not necessarily the same circumstances. You would not replace a relational database necessarily with Hadoop. It can do some things, but you wouldn't replace it. And that really wraps up everything we need to know around the data and data storage and file systems and some of the new techniques.